Very good afternoon to everyone. My name is Metta Sri Venkatsai Priyatam, pursuing master's degree at IIIT Hyderabad. I feel honored to extend my warm welcome to all present here. On behalf of IS Shakti IIIT Student Chapter Earthquake Engineering Research Center, I want to take this opportunity to welcome our honorable guests, faculties, industry people, participants from the academy, research fraternity, and all the students to join the webinar on the topic cold formed steel structures engineering, emerging research and applications. I would like to introduce our keynote speaker for the day, Dr. Mohammad Adil Dar. He is an assistant professor of civil engineering at Pilani, Hyderabad, and an expert in cold-formed steel structures, high-performance steel systems, and lightweighted composites. With over a decade of research experience, he has held a notable positions including as an MSCA fellow at the University of Sheffield, UK, where he led projects on advanced cold-formed steel built-up members funded by UK Research and Innovation, and as a postdoctorate fellow at a National University of Singapore, where he developed rapid installation movement connections for steel and composite structure. Dr. Dar's research output includes over 50 journal articles and 18 chapters and 30 conference papers, reflecting his contribution for structural engineering. He serves as an associate editor for the Hughes Journal of Engineering and is an editorial board of the International Journal of Buildings and International Journal of Structural Integrity. Is actively contributes to ASCE and SSRC committees shaping guidelines in cold formed steel design, stability, and thin wall structure. Dr. Dar's contribution have earned him a prestigious awards, including Marine Crew Fellowship from European Commission and the Ramanujan Fellowship from SERB Indian, establishing him as the leading researcher and innovator in this field. This is a brief introduction about the speaker. Now we start the event and a small announcement for all the participants. If you have any questions, doubts, or clarifications, please do type your queries in the chat box only. We will have sufficient time for the discussion at the end, where Dr. Praveen Kumar Venkatrao, faculty advisor of the student chapter, will lead the discussion. Now, without any further delay, we will turn the time over to Dr. Mohammad Adil Dar. Sir, over to you, sir.
Thank you. Thank you for that very generous introduction. It's my pleasure to address this young and dynamic gathering. If I'm only able to motivate a few professionals out of this group, I'll feel my mission is accomplished. And I would also like to take an opportunity and thank Dr. Praveen Kumar for getting the award for the best student chapter of ISTRUCT recently.
Thank you. Thank you, Dr. Dar.
That's great. So let's get started. As the title suggests, cold formed steel structures. I believe that most of us may not be familiar with the term cold formed steel structures compared to its counterpart, that is hot rolled steel structures.
Dr. Dar, sorry to interrupt. Just can you make it full screen if possible?
Yes. Yeah, is it visible full screen now?
Yes.
Perfect. Let me just hide this. Okay, perfect. So as the title suggests, cold formed steel structures, will be discussing about it in detail. I have dedicated my life towards improving the behavior and performance of cold formed steel structures. And with that brief background, let's get started with the talk. I'll start with my presentation outline to give you an overview as to what will be discussed for the next about 1 hour. We'll start with primary building materials used in today's construction, followed by why steel. That's the main focus of this presentation. Then the various developments in steel, regardless of the type we're discussing, whether hot rolled steel or cold formed steel. Then the types of steel based on the rolling method, and here is where we'll differentiate between the conventional structural steel, that's hot rolled steel, and cold formed steel, followed by the limitations of hot rolled steel. And that's why there was a need for the another type of steel, that's cold formed steel. Then we'll introduce what are cold formed steel members. Again, it will be discussed a bit in detail, followed by why cold formed steel. If we had hot rolled steel, then what was the need for the another alternative? Now, after discussing all the advantages of cold formed steel, we'll also discuss briefly what are the problems associated with cold formed steel members. That's what we try to address in our research, different problems relevant. Then our talk will divert towards a need for built up members, regardless of the type of steel material. Then the design guidance available on built up columns, followed by the need for research on cold formed steel built up columns, followed by the past research on cold formed steel battened columns and limitations. And lastly, the research carried out on cold formed steel battened columns, which paved way for the new improved design guidelines on the same. Now, starting with the primary building materials used, we'll start with concrete. Now, concrete does not need any introduction. It's being used extensively in every nook and corner of the world in any form of construction. For obvious reasons, it's a versatile building materials. Next, bricks. Now, brick masonry structures are also extensively being used, especially in developing countries like India, particularly because of its economy. It's more economical than RC structures. As a result, we see more number of brick mills growing in India. Stone masonry structures, now it may be a little astonishing, but wherever stones are available locally, stone masonry structures still continue to be adopted in mass production. Timber. Timber is one of the oldest building materials used, and it still continues to be used. In the recent times, they have developed what is known as engineered timber or cross-laminated timber, what we may be familiar in the recent times. This is a library building of Nanyang Technological University, Singapore, where the entire structure, except the foundation, was constructed using engineered timber, cross-laminated timber, clearly depicting the example of a modern use of engineered timber in the new generation of structural construction. Next is steel. I'll not discuss much in this slide because the entire talk is on steel. Last but not the least, FRPs. FRP also continues to be one of the emerging materials. I did not include aluminum or other materials because we are talking of primary building materials used extensively. Now, without wasting much of time, why is steel when we have so many other materials available? Why is there the need for steel? In the first slide, we were talking about RCC, concrete. Now, if that's extensively being used, why is there the need for steel? Well, for any structural challenge, steel is the only alternative that we have. For example, long span bridges. Now, wherever we come across such a situation, steel structures are only a viable alternative to such challenges. Now, this is an Akashi Kayakyo bridge in Japan, which stood its test of time, and it's a steel structure. Mega structure in high seismic regions. Now, this comes from my part of the region, J&K. This is Chenab Valley Bridge. Now, the structural designers have access to all the modern materials, but they chose steel. Again, emphasizing the role of steel in modern construction. Tall structures. This is John Hancock Center, Chicago. Again, steel being used. Power transmission towers, due to their high strength weight ratio, they continue to be used in such structural systems. Emergency infrastructure, this is just an example of a bridge being used. These are very small examples of illustrating the use of steel as to what is the role in modern construction. Now, I want to start with posing a question: which material is consumed the most in the entire world? And material means in every aspect. It'll take a while, you may guess and probably note it down. I'll give you a few seconds to ponder upon this. So it's water. Water is being used in every form of life. That makes it the most consumed material in the world. I'll continue with the second question. What about the second most material being consumed after water? Well, it's concrete. Now, I slightly differ with this particular narrative, because when we say concrete, we mean plain cement concrete, which is not true. If concrete is the second most largest material consumed in the world, it's RCC rather than just plain cement concrete, because even in rigid pavements, we use steel rebars to take care of shrinkage and temperature stresses. So it's again steel that takes care of the inherent weakness of concrete, that is its weakness in tension, which makes it the second most material consumed in the world. So again, I'm just emphasizing on the role of steel indirectly in making concrete the second most larger material consumed in the world. Now, steel possesses two important structural characteristics. One is its resilience. So if a structure is loaded till the yield point and unloaded, it's as good as a new structure without experiencing any distress. Now, if it so happens the structure is loaded beyond the yield point, it possesses significant ductility that takes care of from other aspects, particularly from life safety point of view. So these two important structural characteristics gives it the position that it occupies in the list of modern materials. Now, moving on to the various developments in steel, research is going in different parallels. We'll be discussing one where we talk in terms of yield strength, ways to improve the yield strength of steel. So for that, we have what we call as mild steel, then we have high strength steel, then we have ultra high strength steel. But of course, whenever we achieve higher yield strength, it comes at the cost of ductility. So we have to be very mindful when we use high or ultra high strength steel in structural applications. The other aspect is its corrosion resistance. Now we know that carbon steel has one major flaw, that is its poor corrosion resistance, although there are techniques how to get away with that. But sometimes from life cycle assessment perspective, it may not be very feasible to do the treatment for corrosion resistance. As a result, we develop different kind of a steel alloy known as stainless steel alloys. And we have four different types. We have authentic stainless steel, we have ferritic, we have duplex, and we have martensitic steel. They show its application in real world. This is a bridge in Sweden, where if you can see the arches and the cables are made up of stainless steel. And this particular structure, even after 100 years of its service life, will need to replace the deck slab, and the arch and the cables will still be functional given the design loads they were designed for. Now coming to the types of steel based on the rolling method. So we have what we know as hot roll steel. In our common conventional term, we call it as structural steel. Second is cold form steel. Now, these sections would be very familiar. You must have witnessed these particular cross sections in real practice. It's a challenge section, an angle section, an eye section. So these are hot rolled steel sections. And hot roll steel, the term hot roll comes into picture because of the rolling, the production method, where steel is heated up to 1800 degrees Celsius, that is the metal's recrystallization temperature, and then it's passed through the series of rollers, and this is how it gets its shape. Now, this is an eye section. Due to brightness, it may not be visible, but this is an eye section. So this is a process of manufacturing of hot rolled steel sections. Now, what are the limitations of hot rolled steel? First and foremost is the large embodied energy. As I mentioned, we need to heat it to 1800 degrees Celsius. So a lot of energy is involved in this. And given the sustainability considerations, this is a downfall when it comes to comparing different materials. Second is due to differential cooling. Here the tip and the mid of the web cools faster than the junction. As a result, residual stresses are developed. Now these residual stresses, if not taken care of, can be of the magnitude of 0.5 times Fy. So you can imagine your half of the cross section is already preloaded. So this becomes another downfall of hot rolled steel. Next, we have limited cross-section profiles available. So if I take an example, an angle section that I need, that is available to me, if I need a section lower than that, because it's not available, I will not be able to use a lower cross-section, which results in wasteful use of steel as a material that has limited results, and we have to be very mindful about our future generations. Next, different defects, there are inconsistencies in the material characteristics. So you will get some variation in the stress strain plots in hot rolled steel, and again falls on the limitations. Now, what are cold form steel members? We'll start with the definition. Cold form steel members are those structural steel members wherein the shape is manufactured by either a press brake equipment or roll forming machines. Now, this is a press brake equipment where we have a punch and die mechanism. We put a flat steel strip, and in series of events, we convert it into the particular shape of the die. So here is an angle section. These are the series of steps. This is a press brake equipment, how it looks in real practice, and this is press braking in action. Here you can see this intricate profile using a press brake equipment. Now, press brake equipment is used for small projects where you need limited number of sections and profiles. Roll forming machine is this particular machine wherein you feed a steel strip or a steel coil, flat steel coil from one end, and these are series of rollers, and at the end you get the desired shape. These are used for mega projects, and a cold rolling machine is much expensive than a press brake equipment. Now this is a cold rolling in action. You can see this is a flat steel strip. These are rollers, series of rollers, how it converts a flat steel strip into the lippert channel section. Now, here, because the shape forming takes place at ambient temperature, unlike hot rolling, it's known as cold formed steel members. And in hot roll, because the temperature is raised above 1700 degrees Celsius, it's known as hot rolled steel members. Now, what are the key features in cold formed steel sections? So we have thin sections, which results in very accurate detailing. So the offsets are much lower than compared to hot rolled steel, where you have thicker sections. Because of their thin-walled nature, they are galvanized from corrosion resistance point of view. As a result, you get a much better finish than a hot rolled steel rough section. Most of the cases, it may not require any surface treatment, and aesthetically, they do not give any sort of displeasance, and architects sometimes prefer such finishes for their aesthetics consideration. Now, because there is no raising of the temperature to 1700 degrees Celsius, the material properties are nearly consistent. So these are the stress strain curves that I obtained from my PhD research, and you can see a much consistent stress strain response. Next, we get large variety of sections. Now here in cold form steel, instead of extracting strength from the mass, we make the use of the cross-sectional profile. So it's very efficient and effective in utilizing the cross-sectional profile rather than mass of the structure in deriving the strength. It results in lightweight construction that has numerous benefits, particularly from the seismic consideration. Lighter mass, less of seismic force, less of seismic demand of the structural members, smaller members. As a result, it results in lightweight construction. It results in faster construction because of the assembling process that takes place off-site. You bring the modular units to the site, and then it's assembling. It's as simple, in other terms, as a furniture these days that gets assembled at your on-site. It results in higher strength to weight ratio due to its lightweight nature. It results in economy in transportation and handling. Now, given the demography of a country as large as India, you have construction sites off route where conventional material transportation becomes a challenge. Cold form steel being light and compact, it gives an advantage over other constructional materials. Higher yield strength due to cold work, again an advantage, but mind it, again this higher yield strength comes at the cost of ductility, so we have to be very mindful when we take into our consideration the higher yield strength. Overall, in the steel project, we make the efficient use of steel. As I mentioned earlier, steel reserves are limited, so overall we make mindful use of steel as a construction materials, therefore taking into consideration the needs of our future generations. The last but not the least, it is fully reusable and recyclable in nature, and given the global concerns regarding sustainability, it ticks that box head on. Now, I would like to discuss its relevance with reference to the current situation. And if I look at it, post-disaster mitigation, if I take an example of Turkey, in 2023, a major earthquake struck Turkey, bringing devastation in the entire part of Turkey. So we had survivors, and for survivors, we needed robust infrastructure. Cold form steel is apt for taking such challenges head on. COVID-19, makeshift hospitals. COVID-19, we are all, it's in our fresh memory how there was a surge in the number of COVID-infected people, and how the existing infrastructure of the hospitals were not deficit to take on the demand of COVID-infected people, and we needed makeshift hospitals. A classical example is 2,000 bedded hospitals were designed, fabricated, and commissioned in 12 days in China in 2021, clearly reflecting the role of cold form steel in combating disasters, unplanned ones. Now, a different perspective, this is a devastation scene that clearly reflects the devastation caused by collapse of RC structures. Now, here I'm not against RC structures, but just a different perspective. Had a cold form steel structure collapsed, would it have caused this kind of a havoc? Just a perspective. Again, as I mentioned, because of their lightweight nature and because of possessing significant resilience and ductility, they exhibit excellent seismic performance. Now, moving on from the global needs to relevance with reference to India's infrastructural needs. So first things first, military. Now, for military, we have different types of terrains where we need rapid infrastructure. Cold form steel is a viable alternative. And just to give another example of American military that has approximately 52 military bases across the world, they use cold form steel as main load-bearing members for their men on the ground. Now, coming from military to public utility, affordable housing solutions, we have Pradhan Mantri Awas Yojana. Since 2000, there have been postponements and postponements and postponements because the number of houses that they need to construct every day is humongous. It's highly challenging. Cold form steel has great potential to meet up that demand, and it has come to my notice that they have started considering cold form steel as one of the materials for Pradhan Mantri Awas Yojana, but still there's a long way to go. And cold form steel can be used for mass housing as it's well adaptable to such requirements. Now, I'll play a video as to how a cold form steel building is constructed. My apologies, there is no audio. I'll play this. Appreciate that long waiting period for watching this video. So I hope it gave a brief illustration as to how a cold form steel structure is constructed compared to other conventional structures. Now we spoke about all the goody things about cold form steel. Now let's address the main problem. The main problem is premature local buckling. Now, as cold form steel sections are thin-walled, they buckle at lower loads, resulting in different types of buckling. That's the main problem that we address through research. Now, need for built-up members, whenever the low, we have individual sections. So we have channel sections, angle sections, tubular sections. Whenever the load exceeds the cross-sectional capacity of a single profile, we go for built-up members. Now, in hot rolled steel construction, whenever the load demands a large, by adequately spacing apart the cord members, we develop built-up systems for compression, connecting them laterally either by means of lacings or battens. That's how we develop these built-up systems, which are efficient because of their lattice configurations. They are economical because it's not a solid structure. They exhibit better stiffness, and they are aesthetically pleasant, at least from certain perspective. Now, let's move on to the design guidance available on built-up columns. Again, regardless whether it's cold form steel or hot rolled steel. In hot rolled steel, we have the American code AISE 360. We have the European code AC3 Part 1. And we have Indian code IS 800. Now, all these codes are well established, which is evident by the wide-scale adoption of hot rolled steel built-up columns in practice, as adequate design rules are available for non-slender built-up columns. These codes, all three of these codes, they discourage the use of slender sections. And just to give you a familiarization, they advocate for plastic sections, compact sections, and semi-compact sections. And for slender sections, you cannot use IS 800 2007 or AC3 Part 3 or AIC 360. For that, you have a different set of codes. Design of slender sections is excluded in these current codes. Now, for the hot rolled steel, there are certain limits. For example, there's a limit for lambda cord by lambda. Lambda cord is the slenderness of the unsupported cord between the batten plates, and lambda is the slenderness of the built-up section. So a lambda cord by lambda, there's a limit. It should be 0.75 as per AISC 360. That means this should be stockier. Your unsupported cord should be stockier than the overall slenderness. It's 0.7 as per IS 800. From Europod consideration, there's maximum spacing for interconnections. It's 15 R minimum, where R minimum is the minimum radius of gyration for bolted and welded connections. And for batten plates, it's 70 R minimum. For cold form steel, a built-up section comprises of two channels in the back-to-back orientation connected through the web using self-drilling screws. There's a limit for lambda cord by lambda in terms of longitudinal spacing between the screws. It's 0.5 as per AISIS 100. There's a buckling curve contradiction for closed built-up sections. Curve B is recommended as per EC3 Part 3 Eurocode, while as curve C is recommended by EC3 Part 1, both cold form sections. So, what is the need for research to be carried out in cold form steel built-up columns? So, if we look at this particular cross section, this is an open section, but from structural mechanics, we know if we space apart these two channels transversely by means of certain lateral connectors, we get a closer section that exhibits better structural performance than an open section comprising of the same channels. However, for the former, design rules are available both in the American code as well as the Eurocode. For the later, design rules are not available in none of the current codes. Now, can the hot rolled steel design meant for this particular cross section, can it be extended to cold form steel closer section built up columns, or Can the cold form steel built up design rules meant for open section be extended to closed sections? First of all, before we move on, it's important to know the advantages of cold form steel battened columns. So they are simpler to fabricate, simpler connections, flexibility in designing as per the requirement, and can change the intermediate batten spacing. Architectural versatility is also present. And overall, it's material efficient. Now, what are the practical applications? Well, they are used in large structures where we need column-free spaces. And these are some depictions how a large structure comprising of cold form steel batten built up members are used, which has application in ice skating rinks, indoor stadiums, truss girders that are used in footbridges. So again, to give a perspective of the practical application part. Now, moving on to the past research in cold form steel batten columns, mostly plane angles, plane channels, lipped angles and lipped channels were used. And if we look at the relative slenderness lambda chord by lambda versus the overall slenderness, these are the data points. However, if you look at the zone of interest, 0.75 and 200 slenderness is our zone of interest, and we see large number of data points outside this boundary. As a result, we did not see any design guidelines recommended by the past research, which paved way for us to carry out an extensive study on the same. So our experimental study that I carried out at IIT Delhi comprised of cold form steel battened columns composed of plane channels, closed sectional configuration. We varied lambda chord by lambda as 0.25, 0.5, and 0.75. 0.75 was from hot rolled steel design code. 0.5 was from cold form steel back-to-back channels. We had another value with the same intermediate spacing. So we made it 0.25, 0.5, and 0.75. Now we varied lambda chord by lambda in two different ways. In the first way, we altered the lambda chord. That means we altered the intermediate batten spacing, while as we kept the toe-to-toe spacing constant. In the other way, we kept the toe-to-toe spacing, we varied the toe-to-toe spacing and kept the intermediate batten constant to investigate the role of each component towards influencing the behavior of cold form steel batten columns. So we had two different groups. In the first group, we kept the spacing between the battens constant. We varied the toe-to-toe spacing. In the second one, we did the other way around. So this was the test setup that we used, a loading frame for carrying out these actual tests. We used pin-ended support conditions to simulate the roller supports, hydraulic actuator to apply actual loading, load cell to monitor the actual loading. We used LVDT for axial displacement, and we used displacement sensors for monitoring the lateral displacement. We start with the failure modes. So we noted buckling of the cord, and two different types of buckling, where outward buckling and inward buckling was noted in the cord, all in the intermediate battens, between the intermediate batten spacing zones. So these are close-up illustrations where we could see the buckling of the cord at different locations within the unsupported cord length. And this was a peculiar observation that we observed in one of the specimens where a panel distortion was noted. I'll be discussing this in detail in my numerical investigation part. Now, in all the cases, it occurred at the central 1/3 of the column height. And again, it was prominent local buckling. It was in short columns. In the intermediate column, we observed interactive buckling, where the buckling comprised of flexural buckling component as well as local buckling component. In none of the cases did we observe any connection failure, even when the failure of the cord occurred close to the connections, clearly reflecting that the connection detailing and design was adequate. Moving on to the load displacement response. So here you can see all the short columns exhibiting a nearly linear trend till the peak load, then a sudden drop due to local buckling. In the intermediate column slenderness range, we have flexural buckling followed by local buckling, collectively known as interactive buckling. A similar observation in the load versus lateral displacement response. Now, moving on to the performance comparison. So in the cases where we had a constant unsupported chord length of 175 and we just altered the total spacing from 0 to 50, we saw a 120% rise in the axial capacity. From 50 to 100, we saw just a 3.5% rise in the axial capacity. In the second lot, where we kept the toe-to-toe spacing constant and varied the intermediate batten spacing, we saw a 12 and 10, nearly a consistent drop in their load carrying capacities. For more details about the experimental response, results, etc., you can refer to these papers. I'll be happy to share. If anybody requires an access to these papers, we can write to me. Now, moving on to the numerical component, we extended the experimental study on a numerical platform to carry out an extensive parametric study over a wide range of parameters. So for simulating, we use S4R shell element, both for batten plates as well as channel sections. Through a convergence study, we achieved a 5x5 square shell element to be adopted. Material model, we adopted Gardner-Newman's material model. That's an advanced version of Rambo-Rosgood model. Modulus of elasticity 200 GPa, yield strength of 400 MPa. Local imperfection and global imperfections were adopted in recommendation with Schaefer's suggestions. Point-based fasteners were used to simulate the screwed connections, and rigid body constraints were used to simulate the boundary conditions. Now, moving on to the validation part, we not only validated the load displacement response against our own test results, but also the test results of Dabon, who had also carried out a similar research on batten columns. This is a comparison of the failure modes, both against our results and Dabon's results. After achieving a reasonable match, we were confident to extend our numerical model for a full-fledged parametric study that was intended. We adopted a cross-sectional configuration that we adopted in our tests. And the parameters that we investigated were global slenderness that we varied from 10 to 180 in the intervals of 10. The lambda chord by lambda was varied from 0.25 to 1 in an interval of 0.25. The sectional slenderness from 40 to 80, again in the interval of 10. So this is the nomenclature that we adopted, where sectional slenderness, lambda chord by lambda, and global slenderness are indicative. Now, starting with the failure modes in stub columns. So in stub columns, where we had lambda chord by lambda 0.25, what we noted is as we began the progression, we noted yielding in the unsupported chords. As the loading progression increased, there was spread of this yielding across the entire surface. When the lambda chord by lambda increased to 0.5, we saw a same trend, except that the spread was not as extensive as was in the previous case. In short columns, a similar observation was noted. However, again, the spread was more uniform when the lambda chord by lambda was 0.25 compared to when it was 0.5. In long columns, for 0.25 and 0.5, nearly similar trend, not much of difference. However, when the lambda chord by lambda was exceeded beyond 0.5, we saw panel distortion, as I explained in one of the failure modes of the tests. So this was a peculiar observation, and we tried to look into what were the main causes behind. We also noted that in intermediate columns, where panel distortion was noted, and we compared it with our experimental results. Again, we draw a limit where beyond which we start observing panel distortion in cold form steel batten columns. Moving on to the load displacement response, this is for stub columns. So you see a good post-yield strength where we get post-peak response of higher magnitude despite thin-walled nature, mostly because of the stub column nature. In non-stub columns, we observed local buckling in short columns, flexure buckling in long columns, and interactive buckling in intermediate columns. Again, within these three categories, we observed the role of lambda chord by lambda. This is for the short column, this is for the intermediate column, and this is for the long column. Now, moving on to the design considerations. So in the American code AISI 100, we have these are the set of equations that we use for designing a cold form steel built-up column. These are the set of equations from Eurocode, but please be mindful that both of them are applicable to open sections comprising of two elements, the back-to-back orientation. Now, the American code uses two different equations to compute the critical stress, one in the inelastic range, another in the elastic range, whereas the Eurocode uses the same equation. They use different reduction factors. Again, they are meant for open sections and not closed sections. Now, once we used these design equations to compute the design strengths, we observed a pattern. So the pattern was, when the lambda chord by lambda was small, that's 0.25, it nearly matched the design strength computed by the code. As the lambda chord by lambda increased, the pattern was the same, but there was a drop, which increased further as the lambda chord by lambda increased. A similar observation in the Eurocode, where we saw a nearly similar response. Now, what we did is, for smaller lambda chord by lambda, we stick to the current codal provisions. For lambda chord by lambda equal to 0.5, we propose a different curve, which is verified through the experimental results. These are the revised equations where we fine-tune the design coefficients. The same is applicable to the Eurocode. Now, moving on to the main findings and recommendations. So we recommend a limiting value of lambda chord by lambda 0.5. If we exceed it, we see shear deformations due to weaker composite action between the chords. Now, the current North American specification, which is although meant for I sections, can be extended to closer sections as long as we limit the lambda chord by lambda to 0.25. If we use the current codal limit of 0.5, then we have to use the proposed design equations. The same follows for the Eurocode. The recommended limiting value for sectional slenderness is 60, and higher than that gives inefficient results. We recommend that the end batten should be at least equal to the largest cross section for better redistribution of forces. And please bear in mind that our recommendations are limited to cold form steel batten columns with closed sectional configuration, and the adequacy for other profiles needs to be assessed. For further details regarding the modeling technique and other behavioral comparisons, you can refer to these papers. Now, towards the end, I take this opportunity to announce publication opportunities in Curious Journal of Engineering. I am the Associate Editor in Civil and Architectural Engineering. You are most welcome to submit your manuscripts to the journal. Submissions are open. Networking opportunities. ASC is organizing an international conference in India next year, and I am the International Advisory Committee member of this conference. Submissions are again open. I believe that among the attendees may be master's and PhD students, so I took this opportunity to share some prestigious doctoral fellowships and postdoctoral fellowships. We have a Fulbright foreign student program for doctoral program, Commonwealth scholarships, one-year Canada graduate scholarships, DARD Germany, well-known, Eiffel Excellence Scholarship Program France, Swedish Institute scholarships, Swiss Government Excellence scholarships, Marie Curie Fellow scholarships, Australian Government Research Training Program scholarships, and last but not the least, Singapore International Graduate Award for PhD program. In the postdoctoral fellowships, we have Marie Curie postdoctoral fellowships, we have Fulbright postdoctoral fellowships, Humboldt, Germany, Newton International Fellowship, Japanese Society for Promotion of Science, JSPS, Austrian Research Council Early Career Research Award, Swiss National Science Foundation Postdoctoral Fellowship, Lee Kuan Yew Postdoctoral Research Fellowship, Singapore. Last but not the least, Government of Ireland Postdoctoral Fellowships. I thank you all for your patient listening. You can reach out to me at dar.adil@hyderabad.bitspilani.ac.in for any questions or any clarifications. I'd be happy to answer any questions, if any.
Priyatam?
Okay, sir. Thank you, sir.
My pleasure.
Thank you, sir, for
Yeah.
giving a valuable insight. We are able to know so much about the properties and advantages of cold form steel sections and the growing emergence of cold form steel sections as an alternative construction material. The insights of CFS built up members were also very interesting to learn about. Now, the concluding segment of the webinar will cover the questions from the participants who are eager to discuss with you, sir.
Sure. Please go ahead.
Thank you. Thank you, Mr. Priyatam. Thank you, Dr. Dar, for a comprehensive presentation and covering a complete overview of the cold form steel structures, their design and their application part. So we have few questions for you. So let me ask one by one. The first question is, does the cold form steel is used in pre-engineered buildings also?
Yes, it's in fact, cold form steel structures are pre-engineered structures.
Pre-engineered structures.
So they are assembled in that factory, and those modules are taken to the site, and the site, it's only assembling, as was depicted in the video that I showed in between the presentation.
Okay. The second is, why cold form steel are lighter than the other types of steel? Is there any specific reason for that? Is it because of the manufacturing process or something else?
No. It's the thin walled section. Even if you have two hot rolled sections, one is a thinner, another is a thicker. The thicker one will be heavier than the thinner one. So because cold form steel sections are cold bent, if you have a very thick section, then it will be very difficult to bend them, physically bend them. So cold form sections are thin walled. As a result, they are lightweight. Structurally, from structural behavior point, their material characteristics point, they are at par with hot rolled steel.
They're at par with the hot rolled steel sections. Okay. It has been commonly observed that the hot rolled steel sections have a rougher surface finish compared to that of the cold form steel. Why it is so?
So it's a manufacturing process, as I mentioned, that the manufacturing process is what results in that rough finish. However, even in hot rolled steel, they do certain treatments to make sure that we get a much smoother finish. In cold form steel, because it's cold bent at room temperature, and then we do the galvanizing of the steel sections, you get a much smoother finish compared to that.
Okay. The next question is, why the railway tracks are specially or typically made from hot rolled steel sections only?
So railway loading is heavy loading.
Heavy loading.
Yeah, we cannot take chances for heavy loading, when it comes to cold form steel. I would like to make a point here that when I'm advocating the use of cold form steel, that does not mean you can use cold form steel extensively, but majority of the situations where you have light to moderately loaded structures, residential or commercial, cold form steel is a good alternative. Now, if we have something heavy loaded structure, for example, a big industrial structure where I need a crane to be loaded, I cannot go for cold form steel. If I have a very tall structure, I cannot go for cold form steel. So cold form steel has its limitations when it comes to applications.
Okay. So I think the next question is, it is on the same line. If someone wants to use steel for a heavy duty construction projects like bridges and structural beams or the girders, which one is the excellent choice?
There's no excellent. There's only one choice. That's hot rolled steel.
That is hot rolled steel. Okay. From the perspective of durability and fatigue resistance, which one is better?
Now, it's very, what I would say, it's not a straightforward question. So if I talk from durability perspective, material-wise, cold form steel is as durable as hot rolled steel. But when I'm talking from fatigue point, if there's a cyclic response and all, then design is the key. There's nothing like I should go for hot rolled steel or cold form steel. If I design it adequately, regardless of whether I'm using cold form steel or hot rolled steel, if my design is adequate, they're both good.
Okay. The next question is there any limiting slenderness ratio that has been decided for CFS battened columns?
So now, again, we have proposed design recommendations to AISI S100 and EC3 Part 3, Eurocode as well as the American code. But as I said, as of now, none of the codes has published them, in their design book. It's still under consideration. And regardless of that, still, there's a long way to go before we'll have like an extensive cold form steel design manual. So for now, whatever limitations are being given for back-to-back channeled columns, which is there in the code. I think it's 180 is what is being given. But again, as I said, it's all extracted from the hot rolled steel code, not being taken into consideration what happens in slender cold form steel sections.
So this, is there any specific standard or a guideline which is currently has been laid by any of the international agencies?
Yeah, so there are only two standards. So
there
we
are
have the
only
American code, we have the Eurocode. And American code, as I said, still they have explicitly mentioned in AISI S100 that the built-up column, these design guidelines are meant for a built-up section composed of two elements connected in the back-to-back orientation only. So they have explicitly mentioned. Battened column doesn't come into picture there. Eurocode, again, that's currently under revision. We might see the new draft probably in 2025. But to the best of my limited knowledge, not much has been done on this front. But unless and until we have the first draft out, speculations, I would say these are all speculations.
Since we have raised a point on this pre-engineered building, I have seen few of the purlins and the girders which have been placed on the pre-engineered structures, and they are having a S shape.
Yeah,
right?
Z sections.
Z-shaped sections, and they're mostly made up of CFS only, cold form steel.
Yes.
And this tapering sections, especially the columns, they are made up of hot rolled or they are made up of
those are hot rolled.
Those are hot rolled. So it's a combination of both.
Hot rolled steel and cold form steel, where secondary members are made up of cold form steel,
and primary members
and are made up of hot rolled steel. Because welding, and again, as I said earlier, that from heavy duty application where you're doing tapering, so you have to make sure that your thinnest cross section does not cross its capacity. So from that point of view, tapering may not be feasible in cold form steel, because even in cold form steel, you still use screwed connections. You don't use welding, because welding will get it to punch through, because they are thin walled sections. Now, from welding consideration, welding is a continuous joint, while as your bolted connections or screwed connections are discrete joints. So there lies the entirety, that a fixed connection in the entirety and discrete connections at intermediate locations is where the main difference comes. And still, I would still advocate that when it comes to such applications, hot rolled steel is the way to go forward.
The another thing is there any typical range of thickness for especially the cold form steel sections?
So the thickest I have used in my research was 6 mm that I did in 6 mm was what I used in Sheffield, but research shows that you can go up to 10 mm.
And as far as the hot rolled steel sections are concerned, the maximum thickness may go up to?
Hot rolled steel, you have plate girders. If you look at the thickness, you can go 50 mm, 60 mm, 70 mm.
Also.
It again depends upon the application point and the technology you have at your disposal. What kind of technology do you use? For hot rolled steel, I don't think there's a limit per se, when it comes to thickness. But for cold form steel, yes, you have to cold bend it. You have to ensure that the bend is as good practically as you do it on the drawing. You have to make sure there are no cracks at the the bent joint and all. So that puts certain constraints. And again, the kind of rolling method that you use, is it a press brake or is it a cold rolling machine? Again, technologically, there are variations. In one of the visits to one of the industry partners in UK, they had used finite element to simulate minimizing residual stresses while cold rolling a flat sheet. So, I mean, I cannot think of using such a technology in India where they take care of such intricate details. Yeah. So again, as I said, that there's a long way to go, and I would encourage more and more people to engage in research in cold form steel.
So, since you said that, especially the bolting connection, or rather, I'll ask a straightforward question: is it possible to weld the cold form steel sections or not?
It is quite possible. Yes,
it is quite possible.
Yeah, absolutely. But again, as I said, we have to be more mindful and more careful compared to hot rolled steel because of the tolerance consideration.
Yes.
You have less of tolerance here, so you need highly skilled manpower. Yeah, absolutely. Absolutely.
Okay. And when we say that the cold form steel sections are manufactured at a room temperature,
yes,
right? What exactly we mean by that?
So if I have a flat sheet, I bend it. So I'll just bend this. So when I do the bending, this is done at room temperature, right? I don't increase the temperature, unlike hot rolling, where I need to increase the temperature to 1700 degrees Celsius.
So that the material becomes soft, and then
and then you can push it through the rollers to get the desired shape. In cold rolling, you don't need it. I mean, at room temperature, you can just bend it using either of the techniques, either press brake or cold rolling machine. So the rolling takes place at ambient temperature. You don't need a suitable temperature for cold rolling per se.
So before we wrap up, there is a last question. Are there any future modifications that are being considered to be made to the Indian standards to accommodate CFS or CFS built-up sections in detail? Your take on that?
Well, Professor Aurel from IT Madras is leading the IS 801, and he has taken a huge task on his shoulders.
Arul Jayachandran.
Yes, Professor Arul Jayachandran. And I wish him all the best, and hope to see the first draft anytime soon. I'm desperate to see the codal provisions and how do the new codal provisions work for our cases. But since 2015, when I started working on cold form steel, I have been still waiting for the next revision draft out. Maybe in 2025, let's be optimistic that we'll see a new IS 801 draft out.
Okay. One more question popped up. Yeah, how do you compare the economics of a CFS building and a conventional building up to 5 stories?
Now, there are two aspects to this. If I have one building into construction and if I have 1 lakh buildings into construction, economics will differ significantly.
Okay.
My perspective here is that if you use it for mass construction, as is being done in developed countries like UK, US, Canada, New Zealand, Australia, then economics in terms for cold form steel structures can go up to, you can save up to 40%. But again, I'm not putting a number hypothetically. What I'm trying to say is it will put everything into consideration because there are many verticals, supply chain of the materials, the type of techniques that you use. But up to a maximum 40% can be used in a mega project compared to a conventional structure if you use cold form steel the right way.
Okay. One more question.
Are
there any experiments or usage where in strengthening of a hot rolled steel section is done by CFS or even for a built-up section?
Plenty of research works have been carried out where hot rolled steel sections were strengthened using cold form steel sections. Not only cold form steel, hot rolled steel, even RCC structural members were strengthened using cold form steel profiles, different profiles. Again,
Okay.
so you can find them, they are available. But whether there's a design guide on the same, I'm afraid.
Okay. Okay. So I think you have clarified all the questions, and we are really thankful to you, Dr. Dar. Thank you for your precious time.
It's a pleasure.
And now I call Mr. Priyatham to do the further proceedings. Priyatham, it's over to you.
Thank you, sir. I hope the queries of all participants are clarified. Now I would like to call Nisha Singh to deliver the vote of thanks.
You can unshare your screen, Dr. Dar, if you want. Yeah. Yeah.
So, good evening, everyone. I am Nisha Singh, pursuing MTech in Computer-Aided Structural Engineering at IIIT Hyderabad. So, it's my honor and privilege to deliver the vote of thanks on behalf of entire Executive Committee of ISstructure IIIT Hyderabad Student Chapter for this insightful webinar. First and foremost, I extend our deepest gratitude to our esteemed guest speaker, Dr. Mohammad Adil Dar, for his insightful presentation on cold-formed steel structures. The discussion on the cold-formed steel and its application CFS battened columns and the detailed experimental studies involving these were something the participants would definitely have appreciated. Moving on, I would also like to express our heartfelt gratitude to our faculty advisor, Dr. Praveen, for his continuous guidance and valuable suggestions throughout the planning and execution of this webinar. A special mention goes to the IT team for ensuring seamless technical support and to the design team for their creative inputs and logistical support. I thank our program coordinator, Dr. Sunita Palisari, for her continuous engagement. I also want to express my appreciation to all the participants for their active involvement and thoughtful questions, which enhanced the discussion and made this webinar a collaborative learning experience. Lastly, I would like to acknowledge the hard work and dedication of the entire team, whose collective effort has made this event a success. In conclusion, I extend my heartfelt thanks to each and everyone for all the participants and their engagement. We are extremely grateful and we look forward to your continuous support in our future initiatives. Thank you so much, sir.
Thank you, Nisha. Thank you, Professor Dar. Once again, pleasure is all on us. Thank you.
Likewise. Thank you so much. Take care. Have a great rest of the day.
Bye. Thank you.